Okay, geometry students, today we are reviewing Unit 6. And Unit 6 is the kind of the turning point in the year where we stopped focusing so much on triangles and properties of triangles and things like that and turned the corner into the specifics of some of the polygons, and we started off with the quadrilaterals. Okay, so basically here's where we went. We already knew what a quadrilateral was. We had a definition for that. It was any four-sided polygon. Okay, so what we did in this unit is we were looking at all of the different types of four-sided polygons that we had, as well as their properties. Okay, so we started off with one that most people are familiar with, is the parallelogram. Okay, now obviously it is named appropriately. A parallelogram has two sets of opposite sides parallel, and everybody probably knew that coming out of junior high. What we may not have realized was how many properties, in addition to having both sets of opposite sides parallel, the parallelogram had. Okay, so some of the properties were opposite sets of, both sets of opposite sides would be congruent. That is a property of a parallelogram. Both sets of opposite angles would be congruent as well. And lastly, the diagonals of your parallelogram bisect each other. Okay, so that's a lot of different properties that we have there when they introduce the term parallelogram. You have to know that both sets of opposite sides are parallel, both sets of opposite sides are congruent, both sets of opposite angles are congruent, and your diagonals bisect each other. Now, more specifically, if your parallelogram happens to be equiangular, then that will mean that your parallelogram is no longer just a parallelogram. We would call it a rectangle. Okay, rectangle possesses all the properties of a parallelogram as well as being equiangular. Okay, an additional property that pops up because of parallelogram or rectangle is the diagonals are no longer just congruent with each other. They are no longer just bisect each other, but they're also congruent to each other as well. So when the rectangles diagonals bisect each other, you end up with four pieces that are all congruent to each other. Now back to the parallelogram. If your parallelogram this time was equilateral, we would no longer just call it a parallelogram, we'd call it a rhombus. Okay, so a rhombus is going to have all the properties of a parallelogram in addition to being equilateral. And another property that goes along with being a rhombus is that the diagonals are going to be perpendicular to each other. So you pick up a whole bunch of right triangles inside of a rhombus, and of course that opens up things like Pythagorean theorem and SOHCAHTOA and stuff like that. Now, if you happen to pick up properties of a rhombus and a rectangle at the same time, meaning we are both equilateral and equilateral, equiangular and equilateral, then our figure is regular. And the term for a regular quadrilateral is a square. Okay, now that was all of the properties of a parallelogram, as if that wasn't enough. Then we had the figures that only had one set of opposite sides parallel, and those would be the trapezoid. Now, not really much that we know about trapezoids as far as properties are concerned, but it is the four-sided figure with only one set of sides, opposite sides parallel. Okay, if you have a quadrilateral that has no sets of sides parallel, but it's got two sets of consecutive congruent sides, then your quadrilateral is what we call a kite. Okay, an extra property of a kite deals with the diagonals, and the property is that one diagonal is a perpendicular bisector of the other diagonal. And again, since we have the perpendicular going on, just like with the rhombus we did, that opens up all the right triangles, and then you've got Pythagorean theorem, SOHCAHTOA, your trig functions, all that good stuff going on in there as well. Now, I gave you this flow chart back in the day, and if you never did bother to memorize this one or learn the structure of this one, you have probably paid for that oversight dearly throughout the course of the year. You absolutely need to know how these shapes are related, because not only does a shape have its own properties, but it also has the properties of all the shapes that are coming down the flow chart from above it. Okay, so if you can get the structure of this memorized, that is a good chunk of the battle. Okay, now coming back on the next day, we looked at a few more parallelogram properties in there, and particularly what we discussed on the parallelogram was that we had a lot of properties that the parallelogram had, which begs the question, do you have to be informed that you have a parallelogram, or do you have to find all of the properties of a parallelogram in order for a shape to be a parallelogram? Or is it possible that just having a small handful, or maybe even just one of the properties of a parallelogram, will that be good enough for you to determine that you do have a parallelogram? Okay, so we were looking at what exactly is required, and the answer was if you have a quadrilateral and you find any property of a parallelogram, then that makes it a parallelogram, and then all of the properties of a parallelogram do apply, even though they're not marked in the picture. Okay, so looking at all of the properties of a parallelogram, that means if you have a quadrilateral and you can find that both sets of opposite sides are parallel, or both sets of opposite sides are congruent, or both sets of opposite angles are congruent, or the diagonals bisect each other, okay, any of that stuff is going to be good enough for you to say, yes, I do have a parallelogram. And the same argument then spreads and applies to rectangles. In addition to the four main properties that we have for a parallelogram, there's a couple of specific properties for a rectangle. Namely, it is a parallelogram that is equilateral, and it's also a parallelogram that has diagonals that are congruent. If you can find any of those, or either of those two extra properties for a rectangle, then that means your parallelogram is at least going to be a rectangle, and you can go from there. Similarly, same argument for a rhombus. If you know you have a parallelogram and you can find that your parallelogram is equilateral, or you can find that your diagonals are perpendicular to each other, then that means that your figure is at least a rhombus. Okay. Now the bottom line on that is that any one of the properties that go along with a specific shape means that you can kind of shortcut your way into finding that, or establishing that it is that particular shape. Bad news is you still have to know all of the properties, because you never know which one of the properties may be the one that shows up. And if you have only one of them that you have not learned, chances are, okay, Murphy's Law, it will be the one property that you do not know will be the one that shows up, and then you'll be stuck. Okay, an extra property for a parallelogram, as if we needed any other properties for a parallelogram, if you can find one set of opposite sides that is both parallel and congruent at the same time, then that is going to unveil that you have a parallelogram, and then all of the other four properties will apply. Okay, another shortcut here. If you have a parallelogram and you discover that you have any one angle being a right angle, that's going to force the figure into being a rectangle, and the other two properties will apply for a rectangle. Okay, in a rhombus, if you've already established you have a parallelogram and you find any two consecutive sides to be congruent, that's going to unveil that it is a rhombus, and the other two properties of a rhombus will apply. The rest of this was just examples. Then we kind of turned the corner and said, okay, let's quit looking at so much the properties of the sides and some of the angles inside of the polygons. Let's look more specifically at the angles. Okay, so of course, as you should know well by now, in a polygon you have interior angles and you have exterior angles. Interior angles are almost always shown in a diagram. It's almost impossible to have a polygon in a diagram without showing interior angles. Exterior angles, on the other hand, are not always drawn in a diagram. Just be aware that they are always there simply by extending extending the side lengths past the vertex. Okay, then you get an exterior angle. And basically an easy way to remember, or a kind of a textbook way to remember, is that an interior angle and an exterior angle at a vertex are going to form a linear pair. They're going to share a side, which would be a side of the polygon, and then the other two legs of the two angles should form a straight angle. Okay. Now, basically what we have here is we have, fact by fact rules here. The interior angles of a polygon will always follow the formula n minus 2 times 180 degrees. And that result of that formula tells you what the interior angles sum to, okay, how much they add up to be. Okay, so n is the number of sides that you have in your polygon. You plug in n in the formula, subtract 2, and then multiply by 180 degrees, and that'll tell you if you add up all your angles, that's how much they should add up to every single time. Okay, the other side of this argument is on the outside of the figure, and that deals with the exterior angles. The exterior angles in a polygon always, no matter how many sides the polygon has, always add to 360 degrees. And that is a fact, and that's simply the way that it is. Okay, so we worked through some examples, and that was the end of that. Okay, the next thing we did is we took our shapes, our newfound shapes and properties, and took them to the Cartesian coordinate plane. We put them in the graph. Okay, so basically what we have here is we have the same properties that we have had now showing up in a graph, or perhaps we're having to identify them in a graph. So the question becomes, how do I actually do that? What kind of questions do I need to ask myself if I'm trying to spot these properties in a graph? Okay, so some basic ideas here. Okay, how will you know if two sides of a polygon are going to be parallel or not? Well, in a graph, how do you determine lines are parallel? They're going to have the same slope values. That's just a fact of graphs. Okay, another thing that we are needing to know about polygons is whether or not we have sides that are perpendicular to each other or diagonals that are perpendicular to each other. So how would you know that in a graph? Well, quite simply, for two lines to be perpendicular in a graph, you need to have slopes that are negative reciprocals of each other. So you'll figure out one of your slopes, you'll figure out your other slope, take one of those slopes, change the sign, turn it upside down. Did that make it match the other slope? Yes or no? If it did, then you have lines that are perpendicular. Okay, and a big chunk of what we need to know is whether or not we have links that are congruent. And there's a bunch of different ways to go about this. You can use the distance formula, targeting the endpoints of your lines, find out how far they are apart from each other, and then do the same thing for another line segment, and then compare the two. Did you end up with the same results coming out of the distance formula or not? Okay, you can use the midpoint formula in some cases to find overall lengths, or whether or not you have congruences and things like that. Okay, but my favorite way to do it, the way I tend to go about it if I have a choice, is if I have a line that's moving diagonally in the graph. Okay, what I do is I build myself an imaginary little right triangle. Okay, and I use that diagonal line as the hypotenuse of my triangle, and then I can very easily run through Pythagorean theorem, and that'll tell me what the hypotenuse of my triangle is. That gives me my length. Okay, so doing that, I can very quickly and easily arrive at lengths of these side lengths by setting up triangles, and then I compare them to other triangles that I set up in the problem. Okay, and guys, please keep in mind, if you have a line that is perfectly horizontal in a graph, then absolutely you can simply count the length in the graph. If you have a line that is perfectly vertical, then you can absolutely count the length in the graph. If you have a line that is running diagonally in any manner, you absolutely cannot count the length. I know some of you have had math teachers in junior high that said you just count how many grid lines you cross moving along that line from one point to another, but that is absolutely incorrect. Okay, so please do use one of the methods that's on the screen now. Okay, so in the flow chart, if you got the flow chart memorized, it's really pretty easy marching your way through the diagram. In order to determine if you have a polygon, the question is, do you have an enclosed shape built out of line segments? Yes or no? If you do, you can continue to move down the flow chart. Okay, does your quadrilateral have 4 sides? Yes or no? If it does, then you can continue moving down the flow chart. Okay, parallelogram and trapezoid have to do with whether you have parallel sides or not. So we're going to be comparing some slope values in there. Okay, if you have two sets of opposite sides parallel, then you have a parallelogram and you can continue down the left side of the flow chart. If you only have one set of sides parallel, then you have a trapezoid and your shape has been identified. There is nothing else to do. Okay, if you do not have any parallel sides, then you need to check and see if you have consecutive congruent sides. So we're going to look for two sides in a row that have the same overall length, and then two other sides in a row that have the same overall length. If you do find that, then you have discovered a kite, and there's nothing further to look for. Now back to the parallelograms. Okay, once you discover you have a parallelogram, check and see if you have all of your angles the same measurement. Now, in order to be a rectangle, that means right angles. So we are going to be checking consecutive sides inside of our parallelogram to see if we are perpendicular or not. If you catch right angles, okay, in all of your angles, or at least one, okay, all you have to do is prove one in order to be a rectangle, then you do have a rectangle, but you're going to want to continue on and continue checking because you might still have a square. Okay, on our rhombus, we're going to need to check and see if we have sides that are equilateral or not. So we're going to be checking side lengths. Okay, and if we discover that we do have a rhombus, again, we won't want to stop just yet because we might still have a square. And the point here is if you have properties of a rectangle and properties of a rhombus existing at the same time, then you do have a square. Okay, so you need to continue through this flow chart until basically you run out of properties, okay, till you can go no further, or you run into a shape that refuses to have the properties that you need it to have. And that's how we identify our different quadrilaterals in the Cartesian coordinate plane. Okay, so not as much information in Unit 6. Well, I'll rephrase that. There's a lot of information in Unit 6. It just doesn't take me quite as long to explain it this go round. But there's absolutely a lot of information in there. And if you are weak on any of this information, I would absolutely spend a fair amount of time making sure I had it done before the final exam got here.